Hello, and welcome to our example of solving a non-homogeneous boundary value problem with eigenseries. So we will look at the formal solutions to the BVP f double prime plus f equals lambda times f plus cosine of x on the interval 0 to pi, subject to the boundary conditions f of 0 equals f of pi equals 0. First, the homogeneous boundary value problem, if we remove the cosine of x term, is f double prime plus f equals lambda f on 0 to pi plus the same boundary conditions. And we know from before that its eigenvalues are the numbers lambda k equal 1 minus k squared for k greater than or equal to 1, and the corresponding eigenfunctions are phi k of x equals sine of kx. Now the solution to the boundary value problem will depend first of all on whether or not lambda equals lambda k for some integer k. And before we get any further, we need to be able to write cosine of x as a series of these eigenfunctions, namely as the sum from k equals 1 to infinity of some coefficients beta k times sine of kx, and more precisely, beta k would be the inner product of cosine with phi k and L2 divided by the L2 norm squared of phi k. So first we can calculate the L2 norm squared of phi k is the integral from 0 to pi of sine squared of kx, and that turns out to be equal to pi over 2 for k greater than or equal to 1, using some trig integration techniques or a computer algebra system. And so then beta k is going to be the inner product of cosine against phi k and L2 divided by norm of phi k squared and L2. So that's 2 over pi times the integral from 0 to pi of cosine of x times sine of kx dx. We could, of course, calculate this integral directly, again by hand or a computer algebra system, but we could also recognize it as the Fourier sine series coefficients for the cosine on the interval 0 to pi. And it turns out that in an exercise, one of the practice problems a long time ago, we found that the Fourier sine coefficients of cosine were big BK on cosine equals either 0 for k odd or 4k over pi times k squared minus 1 for k even, at least on the interval 0 to pi. So this is really what beta k is. And this gives us all the data that we need to solve the problem, either by grinding up beta k directly or by recognizing it with a connection to Fourier sine series. So let's consider our cases, and the first case is where the parameter lambda is never an eigenvalue. Lambda is not equal to lambda k for all k. Then we know the formal solution to our problem is f of x equals the sum from k equals 1 to infinity of beta k over lambda k minus lambda times phi k of x. And we can clean up this sum quite a bit. First, we know that beta is 0 for k odd, so this is really the sum from k equals 1 to infinity of beta 2k over lambda 2k minus lambda times phi 2k of x. And if we think about what beta 2k is and what lambda 2k is and what phi 2k is, this is the sum from k equals 1 to infinity of 4 times 2k over pi times 2k squared minus 1 times 1 over 1 minus 2k squared minus lambda times sine of 2kx. And that turns out to be 8 over pi times the sum from k equals 1 to infinity of k divided by 4k squared minus 1 times 1 minus 4k squared minus lambda times sine of 2kx. Of course, getting the formal solution as we wrote it at the top of the screen is the most important thing to do, but whenever you're working with series, it's good courtesy to try to clean it up as much as possible. Case 2. What happens if the parameter lambda equals lambda j for some integer j? Now we need to meet this solvability condition, cosine against phi j in the L2 inner product is equal to 0. So let's look at the solvability condition a little further. We need the integral from 0 to pi of cosine of x times sine of j times x equal to 0. Now we can calculate what this integral is, just doing it by hand or a computer algebra system, or going back to what the Fourier sine coefficients for cosine were, if we had done that previous exercise. This integral of cosine of x times sine of jx from 0 to pi is equal to 0 when j equals 1, and it is equal to j times cosine of pi j plus 1 over j squared minus 1 whenever j is an integer that is not equal to plus or minus 1. So what do we see? The solvability condition is going to be met if and only if j is odd. Why is that? When j equals 1, it's clearly met because the integral is 0. If j is odd, then cosine of pi j is minus 1, and that second case just drops out then. In the case that j is odd, we have infinitely many formal solutions, and these are always of the form f of x equals sum k equals 1 to infinity with k not equal to j of beta k over lambda k minus lambda times sine kx plus an arbitrary constant times sine of jx. And of course, we can go through and clean up the first sum as before. It'll be 8 over pi, sum k equals 1 to infinity, k not equal to j, this whole product k over 4k squared minus 1 times 1 minus 4k squared minus lambda times sine of 2kx plus c sine of jx.